Welcome to the Explainer. Today, we're diving into something that's absolutely fundamental to software engineering: structural design patterns. Think of these as the essential blueprints for building code that actually lasts. Here's a question that every single developer runs into sooner or later. You build this amazing application, it works perfectly, but then a new requirement comes in, maybe a new data format, and all of a sudden that solid code you wrote feels like it could just shatter into a million pieces. So how do you stop that from happening? Well, see, the answer isn't about writing more code. It's about how you structure it. It's about arranging it more intelligently. And that's exactly what structural patterns are. They're these proven, time-tested blueprints for creating larger structures out of smaller pieces and keeping everything flexible and reusable along the way. So here's what we're going to cover. We'll start by looking at a group of patterns I call the wrappers. They're all about adapting and enhancing objects. Then we'll zoom out to the organizers, which help us compose entire systems. We'll look at one crucial optimizer for saving memory. And finally, we'll put them all head-to-head so you know exactly when to use each one. First up, the wrappers. And like the name suggests, these patterns all work by wrapping around a single core object. The whole goal is to either change its interface or add brand new features. And this is the magic part. Do it all without ever touching the original object's code. Let's start with the adapter. Its job is really simple. It makes things that are incompatible, well, compatible. The best analogy, hands down, is a power plug adapter for traveling. You're in a new country with your laptop, the plug doesn't fit the wall. You don't go and rebuild the wall, right? No, you just pop an adapter in between, and it bridges that gap. In the world of code, this could be your app, which has been using XML data for years. But you find this awesome new analytics library you have to use, and it only understands JSON. You can't change the library, so what do? You build an adapter that sits right in the middle, translating XML into JSON on the fly so the two can finally talk to each other. Okay, but what if you don't want to change the interface? You just want to add more functionality. Well, that's where the decorator pattern comes in. Think of it like getting dressed. You start with a base object. That's you. Then you can decorate yourself with a sweater to get warmer, then add a jacket on top of that, and maybe a raincoat for water protection. You're just adding new behaviors one layer at a time. The decorator is brilliant because it solves this nightmare scenario called class explosion. Imagine you have a notification system. Instead of creating a separate class for email notifier and another one for email and SMS notifier, and then another for email, SMS, and Slack notifier, no, you just start with one base notifier. And then for any given situation, you just wrap it with the decorators you need. The last of our wrappers is the proxy. And a proxy acts as a substitute or maybe a gatekeeper for another object. A credit card is the absolute perfect proxy. It's not the money itself, right? It's a secure placeholder that controls your access to the real, valuable object, the cash in your bank account. And the proxy is just incredibly versatile. You can use it for something called lazy initialization, so a really heavy object only gets created when you actually need it. Or you can use it for access control, to run a security check first. You can even use it for caching, to save the results from a slow network call, or for logging every request that comes in. It's a really powerful tool for managing how and when another object gets used. All right, let's zoom out a bit. We've been looking at wrapping single objects, and now we're moving on to the organizers. These patterns aren't about enhancing one little thing. They're about arranging multiple objects and classes into these clean, large-scale systems. First up here is the bridge pattern, and it solves a very specific and very common kind of pain. It lets you decouple an abstraction, you can think of that as the what it does, from its implementation, the how it does it. And the whole goal here? To let you change one of those things without completely breaking the other. Here is the classic example. Imagine you have shapes and you have colors. Without a bridge, you'd end up needing a class for every single combination. Red circle, red square, blue square. The second you add a new shape triangle or the color green, the number of classes just explodes. The bridge pattern prevents this mess by creating two totally separate independent hierarchies. One for shapes, one for colors, and then it just links them together. Now you can add a new color without ever touching the shape code, and vice versa. It's a game changer. So what about when you're dealing with tree-like structures where some parts are groups and other parts are individuals? That is exactly where the composite pattern shines. A great real-world example is a military chain of command. You have an army, which is made of divisions, which are made of brigades, all the way down to a single soldier. Composite lets you treat all of them the same way. You can issue an order to one soldier or the entire army with the exact same command. A classic e-commerce problem shows this perfectly. An order might have a few individual products, but it could also have gift boxes, and those boxes can contain more products, and maybe even more boxes. So how in the world do you calculate the total price? Well, with Composite, you just call get price on the top-level order, and it automatically trickles that request all the way down through every box and every item, summing it all up for you. It's seamless. And finally, in this group, we have the facade. Its whole job is to put a simple, clean, beautiful interface on top of a messy, complex system. Think about ordering food from a single app. That app is talking to dozens of restaurants, different payment systems, and a whole fleet of delivery drivers. But to you, it's just one simple interface. That app is your facade. It hides all that crazy back-end complexity, so all you have to do is tap a button to get your pizza. Okay, now for a pattern that has a very different goal. While all the others we've talked about really focus on flexibility and structure, this one, the optimizer, is all about one thing: saving memory. And this is the flyweight pattern. Its entire reason for existing is to let you create a massive number of similar-looking objects without totally running out of memory. And it does this by cleverly sharing as much data as possible between them. Let's say you're making a video game with a huge battle scene. You might need over 1 million particles on screen at once. We're talking sparks, shrapnel, raindrops, you name it. Now, if every single one of those particles was its own complete object in memory, your system would just crash, bam, instantly. So here's the solution. The trick is to split the data in two. You have the intrinsic state. This is the heavy, shared data like a particle's color or its texture image. That stuff gets stored just once in a reusable flyweight object. Then you have the extrinsic state. This is the lightweight, unique data, like coordinates and speed for each particle. That gets passed in only when it's needed. This way, 1 million particles can share just a handful of those heavy core objects, and it saves a ton of memory. Okay, that was a lot, I know. And a lot of these patterns can sound kind of similar, right? So now we get to the payoff. Let's put them head to head and really crystallize the differences so it all becomes obvious. Let's look at our 3 wrappers. When you boil it down, it's all about their intent. The adapter's job is to change an interface to make it compatible with something else. The decorator's job is to add new responsibilities while keeping the interface exactly the same. And the proxy also keeps the same interface, but its goal is to control access to the object. So just ask yourself, am I changing, adding, or controlling? That'll point you to the right one. Now, what about bridge and facade? They both simplify things, but they do it in different ways and almost at different times. A bridge is proactive. You design it in from the very beginning to prevent a complex mess from ever happening. A facade, on the other hand, is usually reactive. You apply it later on to hide a mess that already exists. So one prevents complexity, the other one hides it. And this really leads to the most important point of all. These patterns, they aren't just recipes for code, they are a shared language. When you tell a teammate, hey, I used a facade here, you're not just telling them the solution. You're instantly communicating the entire problem you faced, a complex subsystem that needed to be simplified. They're basically blueprints for communication. So now you have the blueprints for building more flexible, more resilient software. These patterns give you the vocabulary to not just build better, but to communicate better. And the only question left is, what problem are you going to solve first? Thanks for joining us on The Explainer.